Welcome everyone to this third webinar in a workshop series hosted by the Environmental Health Matters Initiative of the National Academy of Sciences. Title of our workshop is Reducing the Health Impacts of the Nitrogen Problem. My name is Kathy Kling. I'm a Tisch University professor at Cornell University and also an environmental economist. I have the pleasure of having chaired the organizing committee for this workshop. For those who have attended either the first or second of our webinars, you'll know that there is a Slack channel that we have opened. You can, if you're interested in participating, you can join that Slack channel by looking for the instructions below the webcast. We found it to be a real fun and interactive way. Lots of people have been providing comments and back and forth discussion. So if you're interested, we urge you to engage in the Slack channel participation. Today, as I said, is our third webinar in the general title of Reducing the Health Impacts of Nitrogen. This is a workshop focused on agriculture and water quality. And my next slide, please. As I said, I am the chair of the organizing committee. There are, I think, 6 of us on the organizing committee. So I hopefully in a minute we'll have a picture of them. We seem to be losing a little problem, have some problem with the audio. I'll give it a second.
Sorry, let me try exiting the PowerPoint and bringing it back up.
No problem. The good stuff all comes later, folks, so you're not really missing too much. Don't worry. I just want to be sure and introduce the folks who organized this activity and give you a real broad-based foundational overview of what was talked about at the first webinar, which, by the way, all of the previous webinars, as well as the full series of 5, will be available on the National Academy's website for anybody to watch, download later. So ample opportunity for you to do that. You want me to try running it from here, Sarah?
Yeah, could you share your screen if that's possible?
Yeah, I should be able to do that. All right. Are you seeing my screen? Are you seeing my screen, folks?
Yes, we can see it.
Okay, awesome. And I'm trying to go full screen. There we go. We got it. Okay, and here's the beautiful pictures I've been waiting to show you. This is the organizing committee. Alina Austin from the University of Washington, Jerry Hatfield from USDA Ag Research Service, Jim Galloway, University of Virginia, Jennifer McPartland from the Environmental Defense Fund, Robin Wilson from The Ohio State University, and Raj Khosla. Raj is going to be moderating today, so once I provide a bit of an introduction and overview, he'll be taking it away. You'll be hearing and seeing lots from him. In addition, and probably most importantly, I want to thank the National Academy staff who have been the heavy lifters here: Carol Laney, Janelle Walsh-Thomas, and Sarah Harper. If any of you have been involved in webinars or workshops, you know how much work goes into them, both in terms of content as well as organizational and logistics, and they've been absolutely remarkable. So a big shout out to them. So our workshop is about opportunities in U.S. agriculture to reduce public health risks of nitrogen in water. Here's just a brief overview of the goals that the Environmental Health Matters Initiative and the academies have for this workshop series. First and foremost, This is meant to be a place for information exchange, and importantly, information exchange between sciences and disciplines that often don't interact very much. This is always a problem, piping in disciplinary walls. And in this particular topic, it's critically important to begin to move on beyond those disciplinary walls and get more both interdisciplinary communication and work. By interdisciplinary, we're talking about all types of science: natural sciences, physical sciences, and social sciences, including economics. And you'll see and hear from a really strong group today that come from all of those different backgrounds. Given a foundation of information, knowledge, and exchange, what do we know? What don't we know? The next goal is then for that to provide a platform for informed discussion. We want to be particularly focused on solutions or potential solutions to address nitrogen problems, solutions that span the entire space: producers, consumers, NGOs, state and federal government policies. And finally, a longer term goal, but one that we hope will get started from this workshop series and many other efforts that are going on, is to accelerate progress in this space. New technology, changes in policy, behavioral change, probably some combination of all of those things are going to be necessary to really get our arms around this problem. As I noted, this is the third webinar in a series of 5. We kicked off the series 2 weeks ago with a foundational set of talks, What is the Nitrogen Problem? And last week, we heard from a series of speakers about possible farm-level actions that can be taken to control nitrogen, as well as incentive and behavioral issues associated with adoption. Today, we're going to turn our attention to landscape-level actions, innovative technologies, and the role of federal policy and particularly USDA government programs in addressing those topics. I'm going to start very briefly, as I said, with an overview of some of the biggest take-home messages from that first webinar, for those of you who might not have been able to join us. I began with a very brief introduction to the fact that the Clean Water Act from 1972 regulates water pollution coming from industrial and point sources. But a substantial portion of agriculture, which covers about 45% of the US land area, does not fall under the regulations, requirements, permitting, and so on from the Clean Water Act and industry. Likewise, the critically important Safe Drinking Water Act, published in 1974, regulates drinking water that comes from our public water systems and providers. But it also has a hole in the sense that over 40 million people who rely on private wells are not under that rubric, and the responsibility for taking care of their own waterfalls on their own testing. Mary Ward gave a phenomenally useful overview and identified that the strongest evidence for a relationship between drinking water nitrate ingestion and adverse health outcomes, besides the well-known blue baby syndrome, is for colorectal cancer, thyroid disease, and neural tube defects. She suggested that future studies of these and other health outcomes should include improved exposure assessment, especially for the highly exposed and at-risk populations. Craig Cox then discussed the extent of contamination of drinking water and noted it has been observed at levels now understood to threaten human health, but that there remains a lot of data gaps, and a lack of a concerted effort to monitor has left us unaware of the full extent of the issue. Ken Kassman then pulled us back towards the farm and discussed how important nitrogen is as an input into the productivity of our food, fiber, and fuel production from agriculture. He called for a national research agenda to better understand how to balance production and environmental quality. Matt Helmers gave us a view of where and how nitrogen loss is prevalent throughout the United States from agriculture, and noted it is very much exacerbated by the set of crops, particularly annual crops, and the aggressive tile-drained landscapes that sometimes underlie them, that have really fundamentally altered the hydrology of millions of acres in the country. Eric Davidson likewise noted that nitrogen leaks to the environment in many places along the continuum of the food system, and that by having knowledge of where those leaks and inefficiencies occur, that can help us design more targeted and effective mitigation strategies. As I noted last week, we identified and discussed incentive and barriers to on-farm adoption of practices. Today, we're going to take that to more of a landscape scale. Before I turn it to Raj for moderating the rest of today's webinar, I want to once again show you the expanse of the agricultural footprint in North America and the United States. The dark green and the light green are all areas where we have a heavy agricultural footprint. The dark green means that more than 50% of the land is cultivated. The light green is anywhere from 15 to 50%. And even many of the brown areas have some limited cultivation. The point here is that the expanse of the problem, where this nitrogen is coming from, is extensive. It covers much of agriculture and much of the United States. So with that, I want to turn now to Raj, who is going to moderate the rest of our program. Thank you all very much for joining us. I know we're going to have a terrific conversation. And again, please join on Slack in any other way that you feel comfortable in sharing ideas as we take this journey together. Thank you. Raj?
Thank you, Kathy, for the wonderful introduction to the third workshop on reducing the health impacts of the nitrogen problem. Welcome, everyone, to our series of workshops. This is the third one among the 5 workshops that we have put together. We have a series of excellent speakers today that are focused on talking about disruptive technologies and how we could tackle the challenge associated with the nitrogen problem and its ill effects on human health. I am Raj Khosla, Professor of Precision Agriculture and Department Head of Agronomy at Kansas State University. With that, I would like to get started with our opening speaker, Stephen Wallander, who's going to talk about federal programs related to conservation and nitrogen management and use. Steve is an economist with USDA's Economic Research Service. With that, Steve, the floor is yours.
Great. Thank you very much. Happy to be part of this and really enjoyed the first 2 weeks of the webinar. So today I'm going to be talking about USDA's conservation programs and how those relate to on-farm nitrogen management and use. And there's a little bit of a, while we're waiting for that slide to get up, there's a little bit of a disclaimer here. I'll just give you my version of it. These are my perspective as an economist, as a research economist. And so in my head, that means lots of supply and demand curves. I will spare you those until the very last slide here. So next slide, please. All right, so there will be 4 key themes that I really want to get across to kind of set things up for today. First, there's a really broad range of possible and actual policy approaches. We'll be focusing on the really big ones and talking about those, but also trying to touch on some of the other alternatives. Second, targeting is really critical regardless of which policy approach you use when you're trying to get things in place across the landscape. And there's a lot of different targeting tools which get used within programs. Third, we heard about a lot of practices last week. We'll be hearing about some more this week. And when we think about which practices actually get put in place on the landscape, It's a mix of policy and a variety of other factors. And the fourth key theme is that even when you've got the policy in place and even when you've got the practices you want to focus on decided, what ultimately happens depends upon some behavioral responses that are really important. Next slide, please. So on the policy setting, we can think in very broad terms on sort of a 2x2 matrix here. We're looking at pollution abatement. We can take a regulatory approach and kind of tell polluters what they need to do, or we can take an incentive approach and provide subsidies to encourage them. We can focus upstream where the pollution's occurring. On the regulation side, that means technology standards. On the subsidy side, that means financial assistance programs that use practice-based contracts. That's the red circle here. That's where almost all of the USDA programs are really focused that we'll be talking about. Some of the alternatives are taking a downstream approach. In regulation, that's emission or concentration standards. On the subsidy side, that would be pay for performance contracts. And some of the practices we've been talking about or we'll hear about today that improve monitoring ability and lower the cost of monitoring could move us in that direction. Next slide, please. So what do those, that red circle, what do those programs look like? Well, on the USDA side, those are called working lands programs. And they have increased in funding dramatically over the last 20 years, from about $300 million in 2002 to over $3 billion per year in 2021. That's the yellow line on this chart. The red line going across that's pretty steady are the land retirement programs. Within those working lands programs, nutrient management and nitrogen pollution abatement practices form a substantial share of the total funding, but they are also focused on a variety of other resource issues. Next slide. So what are these programs? There's a lot of them. I won't go through every single one of them. There's 27 in total, but there's 3 really big ones that dominate total funding and tend to be the focus of most of the research. The Environmental Quality Incentives Program is the biggest of the working lands programs in terms of funding going forward. It is really focused on getting new practices in place from producers and farmers and ranchers who don't have them already. We're talking just about $2 billion a year in funding and another almost $500 million in technical assistance, which is the money for the planning to get those contracts in place. Conservation Stewardship Program works similarly, but it's really focused on taking farmers and ranchers who are already doing the practices that sort of a basic level of practices, and how do you get them to go the next step? And so the term that's used in that program is enhancements. How do you get them to enhance the practices that they're doing? Going forward, it's funded at about half the level of EQIP, but there's also a tail of some contracts under the former iteration of the program that are phasing out over the next couple of years. On the conservation land retirement side, the other big program is the Conservation Reserve Program, which is paying for getting environmentally sensitive land out of production for 10 to 15 years and putting particular cover practices on it. So I want to mention some other programs that are important, but not quite as large. Partnerships are an important deal. We'll hear about some of those later on in some of the presentations. These basically add on to the existing programs by bringing in outside partners who have a lot of local expertise and often bring additional funding to the table, which then increases the marginal incentives that farmers and ranchers have. And so it can really help with adoption. The Regional Conservation Partnership Program works most closely with EQIP, and that's about an additional $300 million per year in federal funding, plus those outside partner fundings. The Conservation Reserve Enhancement Program works with CRP in a similar fashion, working largely with the states to identify sort of key areas and key concerns within those areas. Some other programs I want to mention, we're talking about drinking water. There is a source water protection program. It's only funded at about $7 million per year, but it's very different. It's focused mostly on getting plans in place for particularly sensitive watersheds. There's a new pilot program under the Farm Bill that is just getting in place in some states now that will sign 30-year contracts for expiring CRP acres that are focused specifically on water quality benefits. There also are a variety of landscape initiatives that help focus the EQIP funds, such as the Chesapeake Bay Watershed Initiatives. Now, all of that gets at that lower left part of our policy matrix, those practice-based contracts. There are some regulatory approaches at play here. The biggest one of these is the Conservation Compliance Program. This basically applies to operations that have environmentally sensitive land in production. They've got highly erodible farmland or they've got farmable wetlands, and they're receiving program payments from various USDA programs. And what it does is it says if you want to remain eligible to get those payments and you have this environmentally sensitive land, you've got to do a minimum amount. You've got to get a conservation plan in place, and you have to have some particular activities to address whatever the issue is, which most often is erosion. And the incentives here at play are quite large. Beginning in 2015, the conservation insurance premiums were included in the payments that are covered under the compliance provisions. And annually, those incentives are about $10 to $15 billion per year. So now I want to move on to the second theme, this idea that targeting matters. First of all, we know targeting is necessary, right? We've seen that some of the other studies talk about how there's hot spots, both for in terms of where the nitrogen is coming from and in terms of where the damages are occurring, where there's exposure to the pollution. It's also necessary because if you just take that $3 billion and spread it evenly over the landscape on a per acre basis, you're really not providing much of an incentive. Second really important topic is that targeting is imperfect. A lot of integrated assessment models kind of look at a world imagining that we could just put practices on the landscape wherever is the best, most cost-effective, or most efficient place for them. And that's just not how programs work, which isn't to say targeting's ineffective. It moves you in that direction, but it only gets you partway there. And lastly, in most cases, targeting is using something like a proxy for benefits. It rarely includes both benefits and costs because it's really difficult to come up with all the numbers you need to include both of those in your targeting tools. The largest exception to this is probably the general sign-up within the Conservation Reserve Program. I want to talk about specifically within EQIP what those targeting tools look like, because they happen at multiple places in the process, from the policy being developed in Congress to the conservation being put on the ground. At the beginning, in the rulemaking stage, there's some basic targeting, a little bit blunt, but basically in terms of how you define the program and how you define broad eligibility, you get a little bit of targeting. The second stage is much more informal. There's not really a rigid policy design to it, but that technical assistance we talked about, that conservation planning, involves a tremendous amount of targeting. This is your human capital. These are the people you have on the field in the counties, going out and meeting with the farmers and the ranchers, walking the fields, figuring out what's needed in a particular place and what will fit into a particular operation. And part of their job is targeting, deciding where to spend their time and whom to work with. The third piece of this is where probably the most effective targeting occurs within these programs, and that is that each of these programs is carved up into a bunch of initiatives and priority areas. And it's a mix of input from the headquarters national level and the state offices and state partners and even the county offices kind of deciding what are we going to provide financial assistance for and where. So which practices can you get money for in what counties or what watersheds? And that happens in this third stage. Another stage that's pretty important is during when it actually comes time to apply for the program. If the initiatives are oversubscribed, you have to decide who you're going to let into the program. And the way that's done is with a scoring and ranking process. And that formulas that go into those scores are another really important targeting mechanism. If you have multiple people who want to put practices in place, which ones do you choose? That's how you do it. So what does that targeting look like spatially? Well, going back to the conservation compliance program, this is what the highly erodible land looks like. These dark blue counties have 75 to 100% of the cultivated cropland in highly erodible fields. So that $10 to $15 billion of incentives that are tied to compliance, these counties in the dark blue are where that really has teeth. I mentioned that targeting is imperfect. It depends upon the farmers who are willing to come in the door and ask for the financial and technical assistance, and then ultimately willing to put the practice in place on their fields. And that depends upon the private benefits that they're getting. So when we're thinking about nitrogen, we're typically thinking about, can we reduce the costs to the farmer of fertilizer? And in many cases, this can be substantial, and there's a lot of variation. For corn, fertilizer costs can be up to 40% of their operating costs. And for some other crops, it can be quite less. And so that has an important role to play in the part of the targeting that isn't necessarily under the control of program managers. All right, so on to our third theme here, which practices? What are we talking about? Within the actual programs, the big three that we're talking about within EQIP and CSP, where a lot of the money is going, are cover crops, nutrient management, and conservation tillage. There are some other highly effective practices that are really important in terms of environmental outcomes, such as manure management and riparian buffers. They don't see nearly as much funding as those other three, but again, they can be very important in terms of outcomes. There's a lot here. There's over 170 total practices just in EQIP. A lot of the practices we talked about last week and that we'll be hearing about this week are on that theme of innovation. And so where do those fit into this? Well, I should definitely mention the Conservation Innovation Grant Program here. Once those practices have kind of made it out of the lab or made it out of the experimental fields, you need a little bit of a stage to go through a demonstration process, and you often need some funding to do that to begin to build the economic case for moving them into the big programs. So this is things like bioreactors and digesters and drainage and water management. And so in that sense, the SIG program is a bit of a stepping stone to EQIP and CSP down the road. Looking at those big three practices, we can turn back to something that came up last week and this issue of adoption curves, right? What does success look like? Well, it's hard to think of a bigger success than conservation tillage over the past 2 or 3 decades. This orange line shows us the adoption curve for conservation tillage inclusive of no-till, which is the blue line. Its conservation tillage has gone from about 25% of harvested cropland in the late 1980s to over 70% of cropland now. And that's happened through a variety of drivers. The first of these to come on the scene was conservation compliance in 1985. EQIP in its current form came on the scene in 1996, and what really mattered a lot there was the decision to quadruple the funding for the program in the 2002 Farm Act. And then a bunch of changes happened that were really outside of the reach of conservation policy, and that was the widespread adoption of herbicide-tolerant seeds. One of the biggest reasons for doing conventional tillage is management of weeds. And so the ability to utilize HT seeds in combination with herbicides meant that it was much lower cost in terms of opportunity cost to do conservation tillage. And so a lot of that continued growth was directly related to seed technology. That then had implications on the program side in terms of spending and how things could focus. Conservation tillage funding peaked in EQIP at about $50 million per year in 2006 and 2007, and then has tapered off to about $10 million per year. In the meantime, the expanded focus on soil health issues and increased seed availability and a better understanding of some of the science meant that there was a greater focus on cover crops. Cover crop funding within EQIP is now over $150 million obligated per fiscal year, which is almost 10% of total funding within the program. That then kind of begs the question, what does the adoption curve for cover crops look like? This is from a forthcoming report that will hopefully be released next week. And it's showing by different crops what that adoption curve looks like, or different cropping systems. So one thing to pay attention to here are the corn fields, which are the black lines, and the soybean fields, which is the green line with the triangles. And we see that on corn and soybean fields, we've gone from about 1% of acreage with cover crops in 2008, 2009 to 8% in 2018. We also see that there's some really different adoption rates by cropping systems. It's very low adoption of cover crops within wheat systems, which are the orange lines there. Pretty steady, growing slightly, and higher cover crop adoption with cotton, which are the blue lines. And then on those 2016 corn silage fields, you have enormous increase in cover crop adoption, which from an environmental perspective is really fascinating given the concerns about lower residue on those silage operations. All right, which that then sort of brings me to this fourth topic, which is, okay, we've got the practices we're focused on. How do we link that to the outcomes? The first thing that we think about here, and this is kind of really where the economists come into a lot of this and start to get really excited about these behavioral issues. The first issue is additionality. All subsidy programs, even regulation, is likely to have some degree of non-additionality, some degree to which it's non-binding. And if you think about, going to the grocery store and using your membership card and you get discounts on a bunch of things, some of those discounts changed what you purchased and you picked a different brand, and some of them didn't, and you were just able to pocket the savings, right? These financial assistance programs work the same way. On the higher end, cover crops are thought to be very highly additional. About 91% of the fields that get a payment for cover crops are adopting it because of that payment. Conservation tillage, not surprisingly given what we talked about with HT seeds earlier, is thought to be much less additional. Only about 47% of the fields on the upper end of those crops who are getting a payment, of those fields that are getting a payment, are adopting conservation tillage because of the payment. So the program's still having an impact, but it's less than you would think if you assumed that everybody who's getting a payment is changing their behavior. Once you have an idea that you're changing their behavior, then you start to worry about the direct impacts. What exactly is that behavioral change, right? There are a lot of different ways of doing cover crops. There are a lot of different ways of doing conservation tillage. One of the hardest ones to understand is nutrient management, right? There are many ways to comply with the standards for the nutrient management practice. The key finding here from my colleague Roger Clausen, who's now at NRCS, is that nearly everybody who, essentially the fall application of nitrogen goes to basically zero when you're getting a payment for nutrient management. You may also have some reductions in nitrogen application rates, an increase in post-planting application, but there's more uncertainty around those effects. The last thing we worry about is joint adoption or indirect effects, sometimes called compensating behavior. If you change one thing in a complex production system, cropping system, what else is going to change in response? Sometimes it'll be something that'll move the needle in the same direction you're trying to move it. Sometimes it'll move something in the different direction and hinder your environmental outcomes. This additionality piece is really critical, but it's hard to get a handle on. In order to get an estimate for additionality, we need surveys that let us compare program participants with non-participants, and we need enough of them to sort of statistically be able to construct a good counterfactual for the program participants. So in this chart, what we see is at the high end, you have very high additionality for things like field borders, filter strips, riparian buffers, nutrient management. Lower additionality, as we mentioned, for conservation tillage. Interestingly, you can look at the administrative data for the programs and some of the behavior that happens after contracts are signed and get a good kind of indirect sense of additionality. Basically, the percent of practices that are completed as originally signed on the contracts, the point at which they're signed and the funds are obligated, about 75 to 85% of those practices get completed when they're very high additionality. As that practice completion rate goes up, we tend to be looking at lower additionality practices. And that's not surprising, right? This is kind of what we'd expect given the underlying incentives for farmers to adopt these practices. If the payment is just kind of barely getting them over that positive net returns threshold to be willing to adopt the practice, then if something else comes along, a drought or a price shock or something else, it may be just enough to kind of push them back to the negative side and put them in a position where they're really not able to or willing to put that practice in place. On the sort of indirect effects, joint adoption questions, we're starting to see some interesting things on cover crops. Fields that have cover crops, it turns out, are quite a bit more likely to be testing their field for really important things such as soil organic matter and nitrogen and phosphorus, which hopefully means that they're able to manage it a little more precisely and not have excess application of nutrients. In addition, some findings that aren't shown in this chart but are part of the same report, on these fields with cover crops, continuous no-till is more likely. And on cornfields in particular, manure and compost use is much more likely. All right, so that kind of concludes my 4 themes. Here's the supply and demand curves that I promised you and I held off to the end. And so if there's any questions, this would be a chance to take some of those.
Thank you, Steve, for that excellent presentation. Many of your findings and that of your colleagues got my attention, and I bet it got attention of many other in our audience as well. We have about an hour plus time built in our program to engage in discussion and questions and answers. And if you would allow me, I would like to move forward into our program, into the next segment, which is focused on flash talks. And we have 2 segments in the workshop today. One is on innovative technologies, another one is on governance and outreach opportunities at the landscape level. So with the first one that's focused on innovative technologies, we have lined up 4 outstanding disruptive innovations that land managers and farmers and practitioners should look forward to as they come to fruition. Our first speaker is Kit Franklin. Kit is joining us from United Kingdom. He is a senior lecturer of agricultural engineering and has been the principal investigator of the hands-free hectare that drew global recognition for being the first experiment on the planet that did not employ any human intervention to have a full crop cycle in place. So with that, Kit.
Hi there. Just wait for the slides to load up. And I think we can probably skip straight past the title slide. Okay, so I'm going to talk about precision application of N. And this is obviously a wider part of a wider thing that is precision farming. And with precision farming, we're trying to manage variation across our farms, breaking our farms down from management on a field by field level to a subfield level, and then ideally in future, and some of the work that I work on is looking at maybe even turning to single plant management levels. And what we're trying to do here, in my words, and I say that there's different words for this, we're trying to do the right thing in the right place at the right time in the right way, and I've highlighted there the right amount as being part of that right thing here, which we don't want to put more than we need into the environment. So with precision farming or precision agriculture, we're trying to minimize our inputs and increase sustainability, and that's in every sense of the word. We're trying to be good for the environment by only putting the right amount of product into the environment, but that's also clearly going to be good for the economics of farming, and it's going to be good for the social side as well in terms of the society's view of agriculture, in the sense that most societies around the world want to see a reduction in the use of chemicals and things like that. So it has a truly sustainable angle, ticking all the boxes. Next slide, please. So if we're going to consider putting variable amounts of N into our fields, one of the things we should probably do is consider the background variation that we have in those fields. And the first thing to do there would be consider soil maps. These can largely be done in one of two ways. The first is something like electroconductivity mapping, where we can drag an implement up and down a field and get a very high resolution map of our field. But the information that this electroconductivity map gives us is limited. It essentially tells us the soil texture or the soil type within our field in terms of its clay, sand, and silt levels. And we can infer from that its ability to hold and pass nitrogen to a plant, but it's going to be limited. If we go to a system such as soil samples, in terms of taking samples from the field for lab analysis, we end up with less resolution from what we do, because we're only going to go and take a small number of samples from a field. But we can get a greater level of insight, a greater level of information from those samples, including honing right in on N if that's what we're interested in. And you can see a graph there showing some of the adoptions of this mapping, which is very similar to a graph we've just seen in the US. Next slide, please. A further thing we can do in terms of thinking about our background, if we're farming a crop this year, is to consider what happened to last year's crop, and we can do that by looking at yield maps. Now, yield maps, this is a great place for me to say that this is where, in all these technologies, it always requires somebody with knowledge in the loop, and yield maps are a great example of that, because we can look at a yield map and we can see where in a field yielded well, and we can see where in a field where it yielded not very well. But I could interpret that in multiple ways. I could interpret that I need to put more inputs into the areas that didn't yield very well, but I could equally interpret it that I need to put more inputs into the areas that did yield well, because they will have taken nitrogen from the ground. They will have taken on more nitrogen and depleted that area. So a yield map is a piece of information. It still needs expert analysis to gain full understanding of what's going on, and there's always many factors at play. The reason there's an arrow on the header of that combine there is just to make the point that as combine headers have got bigger, the resolution of this data is actually getting less. So in the 20 years or 25 years that yield mapping has been a thing, its resolution has actually got worse. And again, you can see the uptake in the US of yield mapping technologies, highest in corn production. Next slide, please. So when it comes to actually managing crops as they grow and trying to manage the N in the crops as they grow, one of the things, the main technology we rely on is essentially spectral analysis of the of crops, and looking at the reflected light in multiple spectrums. A lot of them obviously non-visible light, near infrared, etc. We can by analyzing the spectral response, we can essentially manipulate it and look for growth trends. And these are often plotted, as you can see on the right hand side, as nice colorful images with scales where we can see red as bad and green as good. One really one of the main one of these manipulations we can do is an NDVI, a normalized differential vegetative index, and this relies on the fact that a healthy plant absorbs lots of red light to photosynthesize, and an unhealthy plant absorbs less red light. And then inversely, a healthy plant will reflect lots of near infrared light, whereas a unhealthy plant will absorb more near infrared light. And we can use that very basic piece of knowledge regarding chlorophyll and what it absorbs and what it doesn't absorb to calculate a 0 to 1 scale of how healthy our crop is. And then we can use that as in a quantitative way when we apply nitrogen. Next slide. So where are we going to house this spectral analysis? Well, we could house it on a satellite, and the satellite you see there is Sentinel. Sentinel is a pair of satellites, technically. There's 2 of them. They each orbit the Earth every 10 days. So every 5 days, we get a picture from Sentinel. It's covering the whole Earth as it goes. Again, there's an issue with resolution that we get from satellite imagery, just purely because they're a long way away. So every pixel of one of these images is going to be around 10 square meters on the ground. In terms of where I'm from, sat here in the UK, where we get an awful lot of rain, these are limited by clouds. So if we get a cloudy day, we don't get a satellite image, and this can be a real issue if we're trying to apply inputs in a variable way. I can end up with quite literally 6 or 7 weeks where I don't get an image come through that's clear from Sentinel. So it's a bit of although these systems, it's automatic, it's no extra workload for the farmer, the reliability is currently a bit of an issue. Going forward, there's work looking at using radar data coming from satellites to look at biomass growth and judge N requirements based on that. And there's also these new CubeSats that are being launched, where we're going to end up with a lot more satellite passes, maybe 1 per day or 1 per hour potentially even, I guess. And therefore, in time, with these greater number of satellite passes, satellite data will become a more usable thing. In terms of the US, then, I've dragged out some data on this. There's 67% of US farm dealerships have access to this sort of data, and they estimate that 31% of farms are using it. I've already got to conclude. This is way too much to fit in. Next slide, and I will talk really, really fast. We could hang these same sensors off a drone. This gives us the advantage of being lower to the ground, so we're underneath that cloud cover, although there is a problem in the sense that it's an extra piece of work for the farmer to do and relies on a great level input from the farmer. Again, mixed levels of uptake in the USA. These systems aren't so expensive anymore as they were when they first came out, a few £1,000s here in the UK. And now we're quite quick. I can fly my field. I can do a 20-minute flight, and when the drone lands, I've already got the data analyzed, and I can go and apply fertilizer. Next slide. Or we can mount this system on a tractor, and by therefore using the same, we're already driving up and down the field to apply our fertilizers. So why not at the same time monitor and apply the right amount? This is a product called the RN sensor we're seeing in the picture here, and they regularly talk of savings of N of around 10% in case studies of farmers using that system here in the UK. Quite a low level of opportunity to get into these things in the USA, and here in the UK it's not much better. We've only got about 250 farmers in the UK using these systems, despite the fact there's a clear environmental and economic gain to be made from using them. Next slide. In terms of what do we do when we actually then get that information about how much nitrogen we should apply, well, we use variable rate technology. At the moment, this is limited by the width of our machines. So we have very wide machines, and they can only apply one input rate along that whole width of the machine, and that is limiting the precision of our precision farming. We do have auto section, which allows the boom to turn off as it's going across the field, stopping us from getting overlap. And these systems, as you take on GPS guidance, auto section control, and variable rate, they each have an incremental effect on the saving of N going into the system. And again, case studies will show 5 to 10% saving in every case. Here in the UK, where we've got quite small and irregular shaped fields, the savings may well be less when you consider larger areas of land in the USA. Next slide, please. Just one last thing to also think about in terms of technologies is if you're applying organic matter to the field, how do we know the actual the NPK quality of that manure? Well, there are now sensors that, as you're applying manure to the field, can vary the rate as you apply it to ensure that you get an even, uniform spread of nutrient across the field, and that stops high spots and low spots in your field. Next slide. If you consider what you get as an output from this, over time, if you look at the top left-hand corner, you can improve the overall uniformity of your fields. You can improve the way in which crops mature, so you end up with easier to harvest crops by having them all treated the same. And is essentially, as you adopt these technologies in time, you actually need them less because you bring your fields to a level par across them. And next slide for the final slide. So to end, this is where I really do my work, is Hands-Free Farm on the left-hand side, where we're looking at autonomous machines. And the idea of these autonomous machines is to reduce that scale of resolution to be more precise. So rather than be limited with really big machines because someone needs to drive them, let's have many smaller machines operating in swarms. And we're not the only people doing this. Another example is their swarm farm in Australia. Thank you very much.
Thank you, Kit. That was the excellent presentation for opening up this segment of the workshop today. And I know it's challenging to fit everything we have to say in a few minutes. Next up, I have distinguished professor, Dr. Nocera from Harvard University, who has many discoveries. And one among them is something that's equivalent of Haber-Bosch process, or the microbial Haber-Bosch process. And that's what he's going to talk about, his work in that area. So with that, Dr. Nocera.
Okay. Okay, so as was just mentioned by Raj, this is how the world makes ammonia. It's Haber-Bosch. And it's one of the biggest CO2 producers industrially. So for instance, for BASF, that's their largest CO2 producer, this product, fertilizer. So a few years ago, what we did is, and I'll just go through this very quickly, we figured out how to split water to hydrogen and oxygen. And we did that very simply. We took some silicon. This was years of work. We invented catalysts. We coated silicon with catalyst. We could drop it into a glass of water and we could make hydrogen and oxygen. What's interesting is the hydrogen we made was at a very high efficiency. And the reason is we could engineer the silicon to absorb the entire visible spectrum. And then the catalysts were extremely efficient at taking water to hydrogen and oxygen. So we had hydrogen, great. The world doesn't know what to do with hydrogen, doesn't have a hydrogen infrastructure. So we decided to turn to biology and take a carbon fixing organism, have it breathe the hydrogen in. The way we did that is we put hydrogenases into this bacteria. The hydrogen converts to NADPH. And once you have solid NADPH in the bug, you've stored the hydrogen. So you've stored solar produced or renewable hydrogen inside the bug. The bug could then take the hydrogen in the form of NADPH. It can generate ATP. So what you've done is put in hydrogen and basically converted solar energy into ATP. The bug could breathe CO2 in and it could make fuels. And so the blue and red bars are liquid fuel, C5, C3s. The energy efficiency, so solar light into energy efficiency, the amount of fuel we make, we were up at 6 and 8%. So think of the best growing crops, they're 1%. And so we're 6 to 8 times in terms of making a liquid fuel. If we just grow biomass, we could grow it 11 times. Now, this is out of a pure CO2 stream. That's the solid green. But what's interesting is if you just go to air, because these bugs have carbonic anhydrases, while there's a difference of 2,500 in concentration of CO2 from pure CO2 stream to air, we still could grow biomass upwards at 5%. With a 20%, 18% solar cell. If we went up to a 30% solar cell, this number increases. It scales with the efficiency of the solar cell. The bar I want you to concentrate here is right here, this purple bar. That's a solid form of fuel. It's a polyhydroxybutyrate. So here the bug loads itself by fixing CO2 and it makes solid polyhydroxybutyrate. And so what we then said, and that's what's indicated here with this light yellow bar. So this is like a biodegradable plastic. We've basically done carbohydrate loading of the bug in the form of hydrogen and CO2. And so by doing that, what we did is change our strategy from a carbon fixing bug to a carbon and nitrogen fixing bug. And it's a 3-step process. So again, you use my thing called the artificial leaf to make renewable hydrogen. That breathes CO2 in. You store it in a solid form inside the bug. So now it has a solid hydrogen supply and solid ATP supply. And then you can bury the bugs underground. They don't need to see the sun anymore. They don't need any more hydrogen. It's all preloaded. It's like I carbohydrate loaded the bug. Long distance runner, that's what you do. And then the bug underground can breathe in nitrogen, take the hydrogen out of the polyhydroxybutyrate and make ammonia, fertilizer. The key here is that nitrogen fixation is energy intensive. And so most organisms downregulate nitrogen production. So companies like Pivot, what they're trying to do is fool the bug not to get tired, even though it finally does. So it genetically fools the bug, don't get tired, it gets exhausted, it dies. Here, the bug doesn't get exhausted because we preloaded it with a huge amount of renewable energy. And so nitrogen fixation uses 16 ATPs. The bug is super happy. It has its energy supply. It can just make nitrogen on demand. So here we've done lots of farm trials. This farm trial, last panel, what it shows here is that we can replace 50% of chemical fertilizer with this bug, and on the fly, it's making fertilizer. If we load it up with 20% by weight PHB, we can replace 90% of the chemical fertilizer. The bug goes and sits at the root of the plant. It's a slow release fertilizer. So here's the 50% data, this green bar. The black bar is chemical fertilizer. So you see that you basically eliminate runoff because it's basically direct injection into the root of the plant. You can maintain productivity. At 90%, you get 90% less runoff. It's that simple. The thing that makes us happy is by replacing, in this farm trial, we replaced 90% of the chemical fertilizer. That means we save, this farm uses 130 pounds of nitrogen per acre. So we save 225,000 pounds of CO2 from going into the atmosphere. And then as the PHB is degraded, it leaves carbon in the ground. We actually suck 29,000 pounds out of the atmosphere. And that's because we're fixing biomass at 10 times the natural photosynthetic efficiency, which is basically due to the fact that we produce NADPH 10 times more efficiently than a natural plant, because we're doing that all artificially with engineered silicon and the catalyst. And so you actually can fix a lot of carbon. And coming back to this slide, I actually think this is a new opportunity. I know this is beyond this workshop, but what you do, you can fix a huge amount of carbon if you can grow plants basically 10 times faster. And that, I think, is all on the future horizon. But for this presentation, you're able to fix nitrogen with minimal runoff. And then the final thing I didn't tell you, last talk talked about phosphorus. These bugs also fix phosphorus from in polyphosphate from waste phosphate streams. So this is a total renewable organic fertilizer. You can apply it by drip irrigation, and you can maintain productivity like I showed you. So that's it.
Thank you so much. Thank you so much for that very intriguing presentation. Your discovery it's outstanding. I'm sure there are quite a few questions from the crowd. I have some for you as well that we will entertain a little bit later in the session. Next up, I have my distinguished colleague, Professor Arias from University of Berkeley. She's a colleague. We're working together on some of these sensor products that her lab is working on. With that, Anna is going to speak on biodegradable sensors in soil. Anna?
Thank you, Raj, for the introduction, and thank you very much for the invitation to come and talk to everyone here today. as Raj said, we are collaborating in some of the work that I'm going to show today together with Gregory Whiting from the University of Colorado in Boulder. So I'll talk about biodegradable sensors in soil. Next slide. But my group is not a traditional agricultural group. I work on flexible electronics. And what's the idea of flexible electronics? It's a new way of making electronic devices and sensors that doesn't use the conventional fabrication processes used in silicon industry. With these technologies, we are able to make devices with new materials that can be processed from solution as inks. And these materials allow us to use some of the techniques that are used for graphic arts and printing documents, which gives us a technology that is easy to scale in large areas, high throughput. Just imagine how we used to print the newspaper in such large volumes where each page had very customized content. So now here we do that for electronics. One of the aspects of printed electronics is also that the devices themselves are very thin, like the paper, and we only apply the material where you need the functionality of the material. So there's also no waste of materials in the fabrication of these devices. Traditionally, over the years, my group worked, next slide, my group worked on medical devices. And due to the medical devices, we were developing sensors to monitor fluids in the body. And one class of sensors that we developed for medical applications is a chemical sensor. And that's what brought me today here to talk to you about nitrate in agriculture. Next slide, please. So we saw even in this session, I don't need to spend too much time explaining that the nutritional needs for a field or for a crop vary tremendously across the field, and this depends a lot on the nutrients that we give to the soil and the water content. And next slide. And the way we monitor soil really relies on very expensive technology, that usually gives us either information about one specific point in the field, or as the previous speaker spoke, we have to collect samples and take to a lab and analyze it. So next slide. What we have proposed here is to use printed electronics and this technology that is much cheaper than conventional technology to just spread sensors all over the field and increase the density of sensors in the field and monitor the nutrients. We started with nitrate and water remotely. So our sensors are completely passive, and we collect the information from the sensors with an external reader that could be placed either in a tractor or on the arm of the irrigators. And as those machines that are common to the field pass through these sensors, they collect the data. On the next slide, the sensor node looks like this, where everything in the sensor node is made with materials that would degrade in the soil. The sensors themselves can be placed in different depths in the soil, and they're connected to an RFID chip and an antenna that will then communicate with the reader that is above the soil. We have a bunch of these sensors in plant pots, and we are characterizing how fast it degrades. And the idea is that these sensors would just last the age of a crop, or there's also ways that I can see how they would be harvest at the time of harvesting. So the sensors themselves are quite simple. Next slide, please. But we have shown that they are quite reproducible and also quite sensitive to the levels of nitrate and different ions, ammonia, pH, and so on in the soil. The way it works, we have two electrodes, one reference electrode and one working electrode, and we measure the potential across these electrodes. In the working electrode, we add a molecule, which you can see here. It's an ino4, that large chemical structure that you see there, the ion can reversibly attach to that ino4. And when that attachment happens, the potential across these two electrodes changes. And that's what we monitor. We monitor the potential over time for different concentrations of ion. So if you see in the next slide, I'm showing the development of the reference electrode. We also need to make sure that this reference electrode is not sensitive to the ion that we want to measure. In this case, we developed a reference electrode that as we change the concentration of nitrate in the solution, the potential remains constant. And in the next slide, you see the typical results that you would see for a nitrate sensor, where with the working electrode and the printed reference electrode, we can monitor and measure concentrations of nitrate that vary from 3.2 ppm to about 1200 ppm, with quite good sensitivity, as you can see in the plot on the right. We also worried about, if you see in the next slide, we also worry about interference with other ions. So we take a typical report that's for soil analysis, and we look at the ions that are present there, and we do the same measurements. In the next slide, please, where we monitor the potential across these electrodes with different concentrations. Could you please change the slide? With different concentration of ions that would interfere with nitrate in the soil. So next slide. Our vision is to add on to the sensor node, because if we can monitor all these ions in the soil and also monitor gas content in the soil, we could have an impact not only on the agricultural yield, but also on the emission and capture of gases due to agriculture. So I'll finish my talk with the next slide, saying thank you to my students who are very creative and work tirelessly on making this vision work. Maggie, Peyton, and Carol, and Anju, thank you. And also my collaborators, Greg and Raj, as well the funding agency, especially ARPA-E, who has been funding our Pandas project. Thank you very much for the time here.
Thank you, Anna, for that very insightful presentation on biodegradable sensors. Next up in this segment of our workshop is Steve Coleman, who's the Soil Fertility State Extension Specialist at The Ohio State University. And he's going to talk about the potential for perennial grains. Steve?
Great, thanks, Raj. So I want to thank everybody for the opportunity to be here with you today. And I'm going to talk a little bit about, the brief time we have, about perennials and perennial grains especially. So we've, let's see if I can advance here. Okay, here we go. I think I'm going to have control of these, if I'm not mistaken. Oh. Sorry, I think so I'll go ahead and get started. Hopefully we can get this sorted out, but okay, thanks for that. And then I'll start by saying, if we take a step back, we're talking about a lot of nice things here today, but if we take a step back and think about agriculture, we're trying obviously to figure out how we do ag better in lots of ways. One of the pieces is ecological succession. So let's think about ecology for just a second and think about ecological succession. We could talk about that agriculture is by design held in an arrested state of disturbance. You know, this classic theory of we're having, you know, some catastrophic event, and then as time passes, an ecosystem will essentially recover and then essentially settle into a kind of mature ecosystem. Well, agriculture, you know, grain agriculture, 70% of our landscape, cereals, oil seeds, and pulses, really by design, by either a tillage operation or herbicide operation, resets that clock and puts that back in kind of a very early successional stage. And what perennial grains does is suggest that we move that down the ecological rung, maybe just one rung, and put it into maybe a mid-successional stage. This can have tremendous implications in terms of the efficiency of the system, how leaky that system may or may not be. We understand from ecology that in the early phases of a successional ecosystem, in that early successional stage, it's very leaky, very inefficient until plants become dominant, okay? And so we can think about perennial grain agriculture. Of course, this has been a concept the Land Institute at Kansas has been advocating for over 40 years now. We've got you know, two systems as a model system right here. Tallgrass, native tallgrass prairie on the left in Kansas, right next to an adjacent paired field of annual wheat. Both systems, the tallgrass prairie is a zero input system. It's mowed, hay is removed, fed to livestock, and we've got kind of business as usual on the wheat field. They both serve a purpose. They both do things. They appear to be, you know, kind of relatively similar systems until you look below ground. And it's really the root system here in a prairie or any kind of herbaceous perennial system where it's just typically has much greater root exploration, much deeper, and compared to the annual wheat. Those roots, of course, help capture nutrients that are applied. They are constantly pumping photosynthate into the soil and feeding that soil life, making all the magic in soil that happens. So this is soil from one of these paired sites at 1 meter deep. And so this is from that native prairie system at 1 meter next to the adjacent annual wheat field. And you don't need to be a soil scientist if you can see these images, which soil, you know, you'd rather have in your field, right? So, so enter Kernza. Kernza is just a trade name for intermediate wheatgrass. This is a cool season, very productive rhizomatous sod-forming grass. It produces a really nice spikelet that has very small seeds. It can be a very productive crop, can be very tall. And it produces actually a really delicious seed that is, you know, human edible and great in lots of ways. But really, what is a fundamental defining feature of Kernza, of this perennial grain, is the rooting system. And it's quite impressive. And so let's talk about that just a little bit, okay? This is a study that we conducted at Michigan State, and thinking about taking annual wheat, this is winter wheat, versus a perennial, this is Kernza, growing it for 4 years, and just focus on maybe this last year. And at the end of 4 years, we found that that Kernza had almost 5 times as much roots below ground as the annual wheat system. It fostered greater active organic matter pools, and that resulted in more structured soil food webs. So a lot of great things that this plant is capable of doing, particularly for this workshop, is thinking about nutrient use efficiency. And here's we did monitor nitrate leaching across these two systems. That we actually had a few different fertility rates, but this is the compiled piece. And so you can see that there's a fair amount of losses in this blue line, which is a perennial, only in that establishment phase. After that, it really kind of levels off, whereas the annual system, in this kind of constant reset of ecological succession, continues to lose nitrogen. And so over the course of those 4 years, about a 4.5 time reduction, okay? So this work was also repeated in Minnesota. We're looking at 3 different years: maize, switchgrass, intermediate wheatgrass. This IWG is that intermediate wheatgrass. And if we look at that on an annual basis, we see really tremendous differences. This is total nitrate leach on a per year basis. This is an unfertilized low nitrogen over here versus the fertilized about 160 kgs, which would be a typical replication rate for corn, for maize. About a twofold magnitude of difference here. It's pretty impressive. There are barriers to growing kerns. It's not, I just want to temper folks' enthusiasm in terms of what this crop is capable of doing. Primarily low seed, and if you look closely, scrupulously at my last slide or the slide before, you can see this grain component up here. It does not yield a lot of seed, and we know that, and that's a major challenge in terms of having growers be able to plant this crop and make a living. Okay, and we also see a decline in seed yields over time, seed yields and actually productivity over time. So both of these need to be addressed. And we think that there's a lot of value in the idea of a dual use solution, this idea of not just using it for grain, but also for forage. And this has been a very active area of research for us. So 2 sources of income. There's a lot of biomass after we harvest that grain. We could see all this kind of green stemmy biomass that could be used for animal feed, for livestock feed. Okay. We conducted a study across 10 diverse sites across the US and Canada. And here's some kind of hard numbers. Average across all those sites, first, second, and third year, we can see the grain yields. And these are low grain yields, right? So some of our like ancient grains, these grains that are really important, we need at least 1,000 kilograms per hectare to make them kind of profitable. And we're well below that. First year grains are relatively good, and then they really drop over time. So that's a major limitation in the system that we need to address. And you can see there's quite a bit of forage growing there. And finally, we also looked at the implications of clipping or forage harvest in terms of increased root and shoot production. And so we just focus on this. We can see that no clip, summer clip, and twice clip actually stimulated root production and increased nitrogen cycling. So there's a lot of value thinking about this as a dual use system. So I'll wrap up just by saying that kerns is really a kind of a proof of concept, first true commercially viable perennial grain crop, but there's a lot of work that remains to be done, both from like how to grow it, the agronomy piece, marketing. After a grower actually harvests it, what do they do? How do they get it processed and clean? It's just like this whole development of markets. It's a big task. Reductions in nitrogen are promising, but we have to recognize what we're really trying to do with plant breeding is take biomass, photosynthate from the stem and from the roots and partition it more into that grain. When we do that, there are implications for how well it can capture nitrate or how well it can do some of these other ecosystem services that we know and have measured and make us really excited about this crop. So, but I will just wrap up by saying that kerns really could serve a role now. It can function on highly erodible slopes, buffer riparian strips, places that a grower might just put into conservation and not actually have a harvest. So this can actually provide a little bit of off-farm or farm income for some of those. So those areas that we might actually just take out of agriculture, totally put into conservation. So I'll wrap up there and say thanks for your time.
Thank you, Steve. That was an eye-opener for all of us, what perennial grain can do for us, especially the dual-pronged income that you mentioned. And we'll talk more about that in terms of farmers' adoption as we go further into our workshop. We are running a couple, 3 minutes behind schedule. So in the best interest of time, what I'm going to do is we're going to move on to the next segment of today's workshop, which is focused on flash talks and flash talks for governance and outreach opportunities at the landscape level. First speaker we have with us is Roger Wolf. He's the director of Iowa Soybean Association's Research Center for Farming Innovation. With that, Roger.
Well, thank you very much. Really glad to be here, and I've really also enjoyed all the sessions, particularly the last several. How can you not be excited about some of these technologies and tools? Could be a game changer in this space. And so what I want to do, and next slide, please. My slide is, or my talk is about building coalitions to develop and implement solutions. And it's going to be tough to get all these slides in 7 minutes, but I'll do my best. So next slide, please. Okay, so, go back one. Yep. So I really think it's the nexus, really bringing the art, science, business, and policy together. And we think about this. This is really covering the gamut of this workshop, I think, because it's going to take all of us pulling the rope together to make this happen. And I'm not going to read all those bullets, but you're talking about all of these things. I guess the one I would highlight, and folks that know me know that I'm going to talk about watershed planning and implementation. And the reason is I just have a firm belief in that being a process for people, blending of the technology, the blending of the tools, coming up with a plan. All the things that Kit talked about in precision agriculture can apply at multiple spatial scales, and a watershed approach is really a big part of that. It also involves multi-scale systems thinking, and then you think about the blend of the policy and programs, the technologies for nitrogen management, both for agronomy and farming, but also for loss and downstream interests. So now I'm going to share with you some of our experiences and examples that we've had here in Iowa. Next slide, please. Just so folks know who we are, the Soybean Association is one of the largest state-based row crop commodity associations in the U.S. We work for and on behalf of farmers. That is what makes us, I guess, really unique. Our program here with the Research Center for Farming Innovation, we're driving innovations intentionally. We're trying to, kind of follow that good, better, best, right? And that's the curve that we're on. We're always seeking continuous improvement. We really embrace an entrepreneurial approach here. Strong quest for inquiry and discovery. We invest significantly in research internally here at the association, but also externally. We manage the soybean checkoff for those purposes on the production and supply side. There's also another side of the house that does market development and demand-based issues. But it's all about a culture of collaboration, and then this bridging the disciplines, and then seeking outcomes and translating those outcomes into value. Next slide, please. So water challenges upstream for farmers. Just going to gloss over that. I think everybody on the call knows these things, but these are real, and it impacts productivity and crop damage, and we've covered some of that already. Next slide. The water quality challenges in Iowa. We now have nutrient reduction strategies. This is also a coalition approach, a state-federal response to Gulf hypoxia, but not only is it just Gulf hypoxia, but we're addressing the issues locally as well, because we have water quality challenges and concerns here in Iowa, whether we're talking source water, drinking water supply issues, well water. You folks have all covered that already. And then it's a blending of agencies. The DNR manages the permit sites for point sources, and the Department of Ag is really managing the programs for the agriculture sector. This is a relatively new thing, really for the Clean Water Act, bringing these pieces together. And I think there is some progress going on, but is it fast enough? That's debatable. Next slide. As I talked about the watershed approach, this is where the blending of science and technology and research. So here you have on the right side, the performance from and really from peer-reviewed research on all these different practices. And these are the practices that are primarily the ones being promoted in the nutrient reduction strategy for agriculture. which agriculture has a huge goal to meet in that nutrient reduction strategy. We have land use change practices, edge of field practices, in-field practices, and so it's blending. But of course, there's those practices have variable performance, and so how do you account for those kinds of things? And then we try to bring all that information into a watershed planning approach. So that's the management framework. Next slide, please. So we write these watershed plans. You can go to our website. They're all published. You can look at them. We've worked to refine those. But a plan identifies the goals and the best approaches in a really targeted, localized place with a group of farmers, and usually with a lot of other stakeholders involved. Next slide. And to do this, I'd like to talk about the conservation pyramid. This is something that has emerged through the use of the Agricultural Conservation Planning Framework, or ACPF. The folks up with ARS and Environmental Defense Fund helped develop this and launch it. And I'd like to say we're a power user of this tool. It's a GIS-based tool. But all watershed plans need to have a foundation. So all acres, we need to have fundamental good soil health and nutrient management, and then targeted in-field practices, edge of field practices, and in-stream practices. And you look at the performance across all those practices to achieve an outcome. Next slide. So we're trying to scale this up. We got a lot of acres, we got a lot of watersheds. There's about 1,700 hydrologic unit code 12 watersheds. So very small, they're all nested within bigger watersheds. The bigger watersheds are highlighted in bold here. Those are focused watersheds for our strategy. And the reason I'm telling you this is really that we've targeted these plans and focused implementation as demonstration. And these plans and the plans we developed, it took about $900,000 to develop the plans over those 5 years. And then it enabled local partners to achieve secure $38 million in state and federal funds. So some of the programs that Steve talked about earlier today, USDA programs. So next slide, please. And so this is one of the coalitions we've worked on with the Cedar River. It's with Cedar Rapids. They got a regional conservation partnership project. You can see all the different cast of characters. And that RCPP, Regional Conservation Partnership Program, is part of the EQIP program in the last Farm Bill, but it was decoupled in the newest one. This is really leveraging those federal programs with other funding and really bringing funding to bear to support implementation. Next slide. And why would Cedar Rapids be interested? Well, downstream, they've had flooding impacts, infrastructure's been destroyed, big damages. You can see the numbers. They also have source water issues because their wells are along and adjacent to the Cedar River. So you can see the trends on Cedar River water, and that water is in close proximity. So they're worried about their long-term source water issues. Next slide. Why is this important to Cedar Rapids to work upstream? Agriculture is important to the city because that's where a lot of food processing takes place. And these are the companies. Cedar Rapids is the #1 corn processing city in the U.S. And a lot of jobs for that urban area go, work at those plants. Next slide. And this just talks about the Regional Conservation Partnership Program. For the sake of time, I'm going to skip over that. I think you guys get the point. Next slide. And I want to talk about another footprint, or another coalition. This is the Agriculture's Clean Water Alliance. And this is a group of ag retailers. And the reason I want to bring this up is because these are the folks that farmers rely on for their seed, their nutrients, their chemistry, and I'm adding conservation to the mission suite. And these folks have organized, these are competitors that have agreed to cooperate on behalf of a shared soil and water mission. And next slide. And probably the most exciting thing that they're doing today is the addition of conservation agronomists. And really there's a network of these agronomists. And we're trying to bring that piece into the mix so that we're leveraging the retail sales agronomist folks and the relationship with farmers, but also working directly with farmers, trying to help them understand all the practices that we already talked about. And we're trying to scale up implementation in those watersheds. Next slide. And I think this is the last one. So keys to building coalitions, at least from my standpoint, it's about leadership with horsepower. You have to have folks that have administrative enterprise, and you got to think about this at multiple scales. There have to be shared reasons and values, connecting with business and economy, the health and well-being. I think this topic that you're bringing up here today shows that these issues are important. We have to crack the nut on how we're going to do better on this. There's a lot of work to do. And really leveraging the use of research, data tools, technologies, and process. Again, watershed implementation, very important, because then once you have a plan, you have the ability to bring these pieces and parts together to support coalitions. And then you have to have outcomes with value and impact. We got to be making measurable progress on these issues. So I'll stop with that. I know I'm over, so I'll give the floor back to you, Raj.
Thank you, Roger. I really appreciate that. I will jump directly into the next flash talk, focused on irrigated lands regulatory programs in California, from our colleague, Mark LaBelle, who's a social scientist and a professor of environmental science and policy at UC Davis. With that, Mark.
Hello, thank you very much. Hopefully everybody can hear me. I don't see my slides up here yet.
Pulling them up right now. Give me 1 second.
Thank you.
All right, you should be good to go. Thank you.
Okay, great, thank you. Okay, so I am here to talk about the Irrigated Lands Regulatory Program in California, which is an innovative watershed-based approach to regulating nitrogen management in California. I'm a professor of environmental science and policy at UC Davis. I work on cooperation problems and decision-making in agriculture and natural resource management. Next slide, please. You could think of an alternative title to this being non-point source pollution is a myth. And the reason I say that, and I know it's probably kind of an unorthodox thing to say, is that the Irrigated Lands Program shows that it is actually possible to treat ag pollution as a point source with regulatory policy tools and permits at the field level. In other words, you can go to the field level and you can give people permits of some, or other compliance points that mandate the sorts of practices that they use, and it does not just have to be a voluntary sorts of or incentive-based approaches. That's not to say regulations are necessarily the best thing, but at least requires you to think about comparing across different sorts of policy tools in terms of what the transaction costs are of implementing them. When you're looking at agriculture, or the regulations, markets, or incentive-based programs have different transaction costs, and the idea of non-point source pollution is often that it's regulations are costly in the sense it's distributed across lots of different fields or individuals, so it's harder to do than, for example, regulating a sewage treatment plant. But those costs, I would argue, are going down with a lot of these technologies, and these regulatory approaches are out there. Next slide, please. So if you don't really believe me, well, I hopefully can convince you that the California Irrigated Lands Program is an example of a type of hybrid regulatory approach, but there's other ones that are out there. A really important example I point to is the Everglades Best Management Practice Program, where every farm in the Everglades agriculture area has a permit for their nutrient management, and they've seen substantial reduction in nutrients coming out of there. And then the EU Nitrates Directive, which has every single country implementing fairly strict standards on nitrogen management. Next slide, please. So what is the Irrigated Lands Program in California? It's really interesting because it's a hybrid approach. The map you see there are different coalition groups that exist to implement this irrigated lands regulatory program. Under state law, under California state water quality law called the Porter Cologne Water Quality Control Act, irrigated agriculture is not exempt. So the state has the authority at the state level to impose regulations, and the way they've done it is through this hybrid approach. They establish these coalition groups, and the farmer has to join the coalition groups and do the required activities that the coalition groups are there to facilitate. So these coalition groups are collaborative sort of watershed level groups that sit between the farmer at the field level and the regulator at the regional water quality control board levels, and do this type of policy translation process. So it's not a direct permit for every single farmer, but it's this coalition approach. And what are the individual farmers supposed to do? At this point, they submit a farm evaluation plan that says what sorts of practices they're going to put in place. And then they also do some reporting on the amount of nitrogen that they're applying and the different practices that they're using to apply that nitrogen. It's not yet at the point where they are requiring specific limits on nitrogen application, but I think that it may end up going that way. We'll see as they learn more about what the distribution of application rates are and what they think might be the appropriate application rates. And this, of course, is all challenged by the fact that in California, we have a diverse set of agricultural operations, lots of specialty crops, lots of crop diversity, lots of different sizes and types of farms. So it's hard to find one size all fit solutions to nutrient management for all the different agroecological contexts. Next slide, please. So when you're looking at programs like this, you have to do some behavioral research on what drives program or practice adoption and participation in these programs. And this is sort of a summary of a bunch of research we've been doing around nitrogen management in the Irrigated Lands Regulatory Program in California. We're doing in-person meetings, semi-structured surveys, mail surveys, participant observation, a variety of different things that were used to get at it. Next slide, please. And we focus on lots of behavioral questions. So what drives practice adoption? So you can see some of the main practices here that people are adopting, and especially the fact that they're interconnected. So previous speaker was talking about the joint adoption of practices. So in a systems approach, you have to think about the portfolio of practices that farmers adopt, not just one at a time, and synergies between them. Next slide, please. Another key behavioral question: what sorts of barriers do the growers face? You see the number one barrier that the growers say here is government regulations. They don't like being told what to do. They prefer the incentive program. So for them, that's the barrier. But after that, the cost and the uncertainty and the technical knowledge that's needed are some of the big barriers. The uncertainty one, I think, is particularly important and understudied. Next slide, please. And then, what are the effects of the coalitions on learning? So we found that people who participate in these coalitions, even though they are not required to actually change their practices right now or have specific nitrogen management limits, they have learned about how to better do their nitrogen management from the coalition activities. Next slide, please. And so in conclusion, this Irrigated Lands Regulatory Program shows a hybrid regulation and collaboration model that I think is quite interesting, unique for California, and it just demonstrates we need to be thinking about the broad range of policy tools to influence decision making. You need to do research on that to understand how we go, for example, from the really innovative technologies that we saw in the first set of flash talks that are very cutting edge and very promising. But there's lots of those technologies that come up and they don't always spread due to behavioral and structural institutional issues, and we need to understand all that. And then ultimately we need to link all this together, going from the technology and the behavior and the policy to what the actual outcomes are on the ground, in the groundwater at a landscape level, which I think is a big needed next step and calls for interdisciplinary research. So that's it. Thank you very much.
Thank you, Mark. That was a very effective program that you talked about, and a listing of what does it take for a farmer to adopt various practices in terms of behavior. The last talk of today is on how do we engage farmers, so building right on where you left in terms of nitrogen management and decision-making process. And we have with us Greg Labarge with the Ohio State University Extension System. Greg?
Thank you, Raj. Appreciate the opportunity to visit with you about some extension programming that we do here in the state of Ohio. And I think it's not unique to Ohio in the way that we try and accomplish some work from an extension standpoint. Next slide. And actually, next slide. And what I wanted to share with you today was extension. Really what we tried to do is add to the conversation on how farmers view conservation issues, and we work with outside groups and then help farmers understand how others view what they do. We conduct some applied research type of projects and take that data that we generate and translate that into recommendation tools that can be used at the farm level. We try and add value to farmer interest in demonstration and research plots and projects, taking practices to the farm level on their fields with their management and look at the results. Then we identify opportunities where demonstration and research projects lend themselves to measure environmental impacts has become more important in recent years. Next. When we talk about a farmer's view of nitrogen, what we need to understand is that for farmers, nitrogen is a very visual nutrient with an uncertainty about the right rate, but a certainty that when nitrogen is deficient, yields will be reduced. A couple of examples on next slide here. The visual, back up one, please. Basically, the very visual deficiency symptoms of a chlorotic inverted V on the corn leaf during the reproductive and early vegetative stages potentially. And then corn ears can have a nose, and that's the red area that you're seeing exposed on those lower nitrogen rates. And we know as we get out into a field that that's an indication of nitrogen deficiency with both of those symptoms. Next slide. What we have also is a very visual look as we drive down the road in relationship to corn nitrogen rate. Focus on those middle two rows of each one of these pictures, and you see where that yellowing disappears as we have the higher nitrogen rates. And from a good farmer standpoint, a lot of people are looking at what you see in that 240 nitrogen rate. Hits next slide. And with that comes yield response. And so farmers are very sensitive to nitrogen and thinking about reducing nitrogen rates because of that effect on yield. Next slide. Different seasons have different appearances. 2020 corn crop, same kind of set of plots. We see not as good a corn crop as what we had in 2018, but certainly with increasing nitrogen rate, we see an improved coloration, less of the firing on those lower leaves. And as we look at rate response to nitrogen, next please. We see increased yield, although that yield does not max out in what we saw in 2018. Next. and actually next. What we do is really try and take these corn nitrogen response rate trials. This is what it looks like from 96 to 2020 at one of our research stations, and you can see the dramatic difference from year to year in nitrogen response. Some years we are very responsive in relationship to nitrogen. You see where we have a 40-pound nitrogen rate compared to a 240-pound nitrogen rate in 2003 and 18. We have a 100-bushel yield increase. We also have non-responsive years, 2004 and 2, where we have basically no change across the nitrogen rates applied of 40 to 240. And but we also see where we have a difference in what that responsiveness looks like, 80 bushel versus 180 bushel, even though we did not have a response to nitrogen. Next. We've taken approach here in the Midwest as far as taking those nitrogen response curves and putting the economics of corn price and nitrogen price and trying to find the point along that response curve that makes the most sense from a economic standpoint, because we have all these other variabilities and factors. This has been seen to be a fairly recent or fairly good way to go about nitrogen recommendations. Next. And if you kind of focus on the charts at the bottom, basically with the blue line, what you're seeing is a crop yield response. You have the green line, which is the fertilizer cost. And then in that you have the net returns as the red line that gives us the rates that you see there of MRTN for 176 in 2020, 189 in 2021. Next slide. And working with farmers on their fields, next gives us a great opportunity to look at some things like in-season application of manure to corn and wheat. This reduces the seasonal nitrogen input and has some economic benefits. Next. And we have a field here that was under those two different systems where we talk about fall applied manure and 28% in season compared to just an in-crop application of manure. Next. And farmers will often focus in on the yield component, and that's very important from their standpoint. Next. And what we can do from an extension standpoint is add some other data collection to that. Plant health, document what the input is as far as total nutrient, what the status is in the soil at different periods of time, look at the economics, and finally take a look at water quality. And next, please. And next. And we do have in Ohio a good resource, edge of field sites that give us an opportunity with 20 paired field sites to look at what's happening at the edge of fields for different practices. Next. And this is what we've been seeing since 2011. We have a history for some of these sites going back that far. These are the average annual losses as far as nitrate in pounds per acre at the edge of field. Certainly, as we share this with farmers, we can think about a 100-pound loss and put that in economic terms that hopefully we can change management systems and approaches. Next. I wanted to pull this slide in because from Linda last week, and what I wanted to point out is that farmers have an information network that they develop. And they involves all of those folks that you see listed there. And really it's the consistency of the message they hear that impacts what direction they take. And sometimes there can be competing messages or different messages that cause them to take issues that they have identified for their operation. We work through a variety of people, and we try to meet people where they are and take them to that next level and think about that ideal of continuous improvement. Thank you.
Thank you, Greg, for your excellent engagement of farmers in reaching a decision-making process that they utilize for nitrogen. And I totally agree with you that tolerance for nitrogen deficiency is very low because that it's totally certain if you apply less, you might take a hit, but tremendous amount of uncertainty if you were to, how you manage nitrogen. What I'm going to do, looking at the clock right now, that I will go directly into the review of input that we have been collecting since last week. And I'll just share with you a couple, 3 slides, the input we have received from the field on the 2 flash talk segments that we had today. And after that, we have about an hour today that we will field questions from the audience who are on webinar. Please continue to incorporate your questions. We'll entertain those from Slack. And for those who are on the panel on Zoom, please raise your hand should you want to share a comment or want to ask a question for discussion to the panel. So based on the input we have received on the new technological solutions, here is the summarized list that there is a need for soil, groundwater, and aquatic sensors to track leaching. And not that many of these sensors don't exist today, but as Professor Arias mentioned, they are cost prohibitive many times. Green technologies, fluorescent sensors, whether they're mounted on drones to quantify crop stress and using that into translating for nitrogen management decisions, infrared sensing for nutrient sufficiency. There was a very good presentation by Professor Scheppers in second workshop last week, where he talked about the inability of the sensors to assess the deficiency of nitrogen in plants. All they can do right now is whether or not plant has sufficient. So what if the plant has more than sufficient? Can sensor pick that up? Unfortunately, not with our current technology. New biostimulants, and we heard a couple of presentations today on the need for coalition, forming data cooperatives so that we can take advantage, harness the power that big data has in reaching decisions that are cost effective for reducing N losses. Next, please. What are the behavioral approaches that we need to engage farmers with the existing technological tools? I know I've heard this input several times before, that could we take away the complexity? We realize that agriculture in the last 20 years has changed significantly, where lots of digital tools have come to the market, with many times have overwhelmed our farmers and practitioners. So could there be user-friendly, or as this input suggests, license-free GIS modules where farmers can employ that for uploading their field-level information? Bioreactor implementation. Our first speaker, Steve, spoke about that as a part of the Conservation Innovation Grants and other programs that USDA NRCS services have offered to practitioners and farmers. Setting up and supporting group of farmers to innovate together. We saw one of the indices among many that Mark LaBelle showed in what has worked or has not worked in California. Have farmers commercial crop advisors, including conservation practices and recommendations. Next, please. What are the new markets, policies, or collaborative efforts that we can employ in engaging farmers with the existing technologies? So carrying on that thought process, cost share for small farmers to implement bioreactors. That's exactly right. We have quite a few large farmers, but then we also have medium and small scale farmers. And could there be programs that enable sharing of cost for the implementation of these conservation programs that include bioreactors? Another input on increase in funding and access to USDA 590 program. I know we have among us economists from USDA, so we'll discuss further on this input. And watershed approaches focused on diversity and setting limits. Need markets for small grains to encourage their use in rotation with row crops. All very excellent inputs that we have received. Next, please. Okay, so those were all the inputs that we have received on the 2 segments of the Flash Talks and the speakers that we have had. I would now like to go ahead and open the floor for discussion, comments, and any questions that we have. Okay, while we wait to hear for questions, I would like to open the floor by asking a question. And this is meant for Steve Wallander, and others are welcome to join in. Steve, in your presentation, you talked about that there was no change in end rate application or timing of an application. The 2 very big drivers of when we think about end management. Were there any follow-up to figure out what were the reasons limiting that?
Thanks for that question, Raj. One thing I didn't have time to point out, really that's sort of a question of statistical significance. The point estimates for the sort of expected change in application rates is actually fairly large, fairly meaningful reduction in application rates. Same thing for the increase in post-planting application. There's a fair amount of statistical uncertainty because of both the data and the statistical methods used. So I would say we can't, statistically, we can't rule out the probability that there's a 0 effect, but our expectation is that there actually probably is one that's sizable. And so in terms of follow-up research on that, I'm not aware of any yet. I think one of the discussions that came up on the Slack was talking about this challenge of, how much do the nutrient management plans matter? And they all contain different things. And so part of that statistical uncertainty is because some plans will call for post-planting application and other ones won't.
Okay, thank you. We have a question from Slack for Professor Nacera. It reads, this new technology for fixing nitrogen sounds really cool, but what is the cost presently, and what is the scope of bringing this down in the future?
Yeah, we've done a lot of cost analysis. So for this, right now we're well below all organic prices. So I think that people here would know more, but the one I found was basically $3 for chicken manure. And so our cost here, we're up at around 90 cents, and it all comes down, and then I believe the cost can go much lower. So it comes down to how dense a culture you can grow. So a minimum volume, high density reactor, the denser the culture, the cost just starts dropping tremendously. And so one thing we're working on is these high density reactors. I would just say in general, that's true of any anything, is you want as high a density in terms of organism as possible. But on another note, so we've already done farm trials where this is cost competitive, but farmers aren't going to go to something that's just cost competitive if it already works. So the other drivers are the reduced nitrogen runoff and then carbon, if that ever becomes important to farmers.
Okay, thank you. I see one of our panelists, Robin Wilson, has her hand up. Robin?
Yes, hi. Thanks everyone for the great presentation so far. We've been having some side conversations in Slack, so folks might be watching there, but I did have a question that's kind of for Steve, but I think broadly for everyone. I had asked Steve, and we went back and forth a bit about the potential for better targeting within our existing federal programs. And so one of the themes that I think came out of one of the prior workshops was, maybe we have the right technologies and tools and we have motivated farmers, but we have kind of broken systems. And so thinking about the way targeting is currently done and the fact that it's not necessarily getting at some of the right people or the right operations or the right areas in terms of addressing nutrient issues. What are other ways we could target? What's the possibility of that happening through current federal programs or other existing structures and institutions? And I'd just be curious if folks have thoughts about that, because we talk about that a lot as far as improving our targeting, both to physical risks, but also to the people who need to be engaging more in conservation.
Sure, I can offer a little bit of a quick response to that. I do think as better spatial data, even some satellite data comes up, that creates the opportunity to do sort of broad targeting within programs like what we saw in conservation compliance and like the scoring tools, right? The trick there is you need data on all fields in order to be able to score them in these, whatever the targeting tool is. I think there's also quite a bit of more informal targeting that goes on through the local partners and through the local conservationists. They do try to engage populations that they know would be high impact and that might not be as willing to be engaged or as traditionally engaged. It's pretty challenging. And I think, part of it is the personality of the conservationists, but I think a lot of them really try demonstration days and other things and reaching out specifically to people. We're also learning a lot about sort of the behavioral targeting and behavioral interventions from other areas. These tend to be pretty low cost, things like peer comparisons. They also tend to have fairly small effects. And I think what we're seeing in some studies that are really trying those is that they may not be as effective in a business setting with operations as they are with consumers, so sort of consumer water use and electricity use. So many operations will have pretty good idea of what they're already doing. But it may be a case that we're still trying to figure out the right way to do those behavioral interventions and that behavioral targeting.
Okay, thank you. I see a question popped up, and this is for Professor Nocera and Arias. And it says, wonderful work. And the first segment is for Professor Nocera. What is the downside of engineered nitrogen fixing microbes? And then the second half is related to the sensitivity of the nitrate sensor. Can you determine differences in 0.5 part per million versus 3 part per million, or measuring nitrate versus nitrate nitrogen? So first Professor Nocera and then Anna.
Yeah, the downside is GMOs. So we don't do GMOs. We use synthetic biology and we engineer the organism and we see how it works. And then we go back and we optimize the microbiology so that, for instance, loading it up with its energy supply with genetic engineering, I can go to 90% by weight. I can put a huge energy supply in it. But then you can see how the organism's working. And so everything I told you was not engineered, but then we optimize the microbiology to get it to uptake to 20%, for instance. So avoid all GMO at all costs is what we do, but we use engineering to guide the microbiology to optimize the organism.
So I have a follow-up for you, building on that. You're right. You make a point that this is not a GMO, and you can site specifically produce nitrogen that can be taken up by the plants. What about the leaching element? Because at the end of the day, you still have this bacteria-based or modified organism-based mineral nitrogen. Is that prone to same levels of leaching as what you would use at urea ammonium nitrate?
Yeah, we need to do more studies on this, but the data I showed was looking at nitrogen content in the soil. So we didn't see much nitrogen content in the soil. It's all going to the plant, sitting at the root of the plant. But we need to do more studies on that. But whenever we just do the analysis of soil, that nitrogen's missing, and the only nitrogen's there is from chemistry. And actually something kind of comical is just in general, there's so much nitrogen in the ground. We actually have trouble finding plots where there's not so much residual nitrogen that we can get a good control experiment. But if you think about what I'm saying, we're taking nitrogen from the air, phosphorus from waste, and carbon from the air. So this technology allows you, and we've done this in greenhouses, totally soil depleted, nutrient depleted soils. And this actually puts it from the air and waste streams back into the soil. But it's unbelievable how hard it is to just do a farm trial that doesn't have way too much nitrogen in the soil.
You're right. As a precision agronomist whose work has focused on nitrogen my entire career, I totally understand what you're saying, and that's why people who are engaged in nitrate research, such as we work on several years worth of work where we mine nitrogen from the fields before we start implementing nitrogen response there. I think I have a hand that raised by Roger Wolf, who wants to weigh in on this question. Roger?
Well, yeah, I wanted to go back to the previous question about targeting. And one thing I want to add, with watershed planning, we can use predictive modeling to inform how we write those plans, and we do that a lot. But we also use active water monitoring. So as we implement things, so that's kind of in the validation frame, like the precision agriculture. So we're measuring after the fact. So we can use water monitoring at multiple scales to help refine how our implementation is going. And then I want to add that, when you start thinking about ecosystem markets and potential marketplace, and will there be a marketplace for carbon, and can we connect that with water quality? If there's a cash flow system in there, then we can pay for performance, which is what Stephen highlighted. And I think if you take a combination of what Mark talks about in California, and you take a combination of the programs, and you take a combination of predictive and validation monitoring, we can do a better job of refining. So I'll stop with that.
Thank you, Roger. Well said. I want to circle back to Anna about the sensitivity of your sensors.
Right. The sensitivity of our sensors is, I thought, pretty adequate to soil levels. I'm still learning. So we went to very low concentrations of nitrate, and then that's what we are reporting on the 3 parts per million. And we worked a lot on the reference electrodes in order to make sure that when we are at the higher concentrations, we have as good a sensitivity as when we are at the lower concentrations. In terms of detecting other ions and differentiating them, the best way to do that is to have multiple sensors and then work on an ionophore or a membrane that selects for that ion. And that has been our approach in order to develop the other ions, like ammonia and pH, for example. We use just different ionophores and just add sensors to it. Hopefully that answers the question.
Yeah, thank you, Anna. I mean, I recall your last slide where you would like to have a desirable sensor fusion network where you have different ion-specific sensors built into one larger node. But till we don't have it, let's say we have the sensor that we're working on, you are working on right now, or we all are. Would it differentiate till then, or would it provide a sum total measure of nitrogen that it sees in the soil solution?
It would give you a quantitative measurement of the nitrate concentration. In order to, on the other sensors that we have, that we started working on, they are different. They are not necessarily chemical sensors as the nitrate is. So that's also part of the design, to pick your selectivity or your selection material or mold according to what you want to monitor.
Okay, thank you. I have a question from Slack for Mark. Have you measured in California nitrate loss reductions on the farms participating in the state's hybrid regulatory or collaborative programs compared to non-participating farms?
Yeah, thank you. I did put an answer to that in Slack, but I'll say it here again. So, you know, in the coalition group areas, all farmers are expected to comply. So it's, they actually report quite high compliance rates. So 90% and over compliance rates, which is good. So when they, when they go for non-compliance, they're talking about targeting 10 farmers. Things, small numbers. So it's hard to get a control group to say they're participating in the program versus not. And also, this is something I think is worth pointing out to this group, which is, how to link practice adoption at the behavioral level and rates of nitrogen application at the behavioral level to what is actually lost and what ends up in the groundwater. I think is a place where we need a lot of research. I think if we could really get that link strongly established, then we could do more of a systems level analysis. It starts from the policy to the behavior of the farmers to what we would expect at the landscape level in terms of nitrogen pollution sorts of outcomes. So like I saw some, like one of the presentations earlier had a nice list of like percent reduction from each type of practice. I think it was in corn. Stuff like that I think is promising for kind of getting that systems level view.
Thank you, Mark. I have another question from Slack coming for Steve Coleman. Any ideas on whether strategic grazing of Kernza could stimulate grain production?
Yeah, thanks for that. So we haven't really done a lot of work with grazing just yet. It's all been kind of a simulated defoliation or a haying type of event. It's all mechanically done. We know that this grass, intermediate wheatgrass, is extensively grazed in the Great Plains and Intermountain West region. So we know it's highly tolerant to grazing. We expect that some of those same responses that we're seeing in terms of stimulation of productivity with grazing will be, or with that haying will be consistent with grazing. So we have some on-farm grower trials going on right now, but just starting those. So we don't have very good information on that yet, although it's a work in progress.
Okay. Kid, I have a question for you related to precision N management. You and I both know that if you look at the studies across the board, it has been documented widely that precision nitrogen management has a very positive influence in terms of enhancing nitrogen use efficiency. But the results are mixed when you look at increase in nitrogen use efficiency coupled with increase in production. And I know many farmers that I work with, they look at production because that's tied up directly to the bottom line. In your experience, and you can share from Europe, but in general, is that one among many reasons you think that it has not picked up as much as we would have liked to? It has been around now for 20 some years.
Yeah, I think for me, I always come back to the reason adoption is low is because of a kind of a lack of really credible business case for a lot of precision farming technologies. And I'm going to now tell you some fairly uncredible stats. I work closely with a company called Precision Decisions in the work that I do in automation, and they are the UK distributor of the RN sensor. And across their sort of 250 units that they have out on the ground, they believe they see yield increase of 2 or 3%, so completely negligible really in wheat. But what they always report is a reduction in nitrogen input. So the farmers are generally satisfied that they're not necessarily seeing any more crop, but they are putting less nitrogen out of the shed or out of the tank. But frankly, I think the biggest barrier to uptake of any precision farming tech is always a business case, and in the UK, to come on to where adoption has happened, it's often been backed by small business sustainability grants, where essentially farmers can fall into being a small business category, and they can apply for 50% of the £20,000 the end sensor is going to cost them. And that's sort of the route to getting these things on farm. They're generally pretty satisfied with what the result once they've got it, but they won't take the leap without that financial help in the general case, unfortunately. The one that really frustrates me is the less complicated one, which is auto section control on a sprayer boom, on an applicator boom, and the uptake of that is so small. And again, if you widen this out beyond nitrogen, you think about pesticide application. Here in the UK, you have it may be a 10 or 15,000 pounds option to have auto section on a new sprayer, and on a reasonable size farm, you could save £50,000 a year in chemicals that you're putting into your farm. But we haven't been very good at telling that story to the farmer.
Right. Well, this is where Greg comes in. He interacts so much with farmers, and I was just wondering, what if this is a what if scenario? Hopefully in future it becomes a reality. So two questions are going through my mind. One, Stephen, are there similar programs, what Kit described, that they have one in UK that could get farmers' attention? And then I have a follow-up for Greg.
Well, certainly there's the traditional financial assistance programs. Precision Ag gets more of a focus within the conservation stewardship program than it does within EQIP. It does get quite a bit of attention there. And there also are definitely efforts for demonstration projects and things like that. And I think people do look to folks like us at the Economic Research Service and folks at the Agricultural Research Service to try to come out with numbers and sort of say, well, how much is this going to save farmers? And the real challenge, and I think anybody working in extension knows this, right? The real challenge is tailoring those numbers for the farmer, right? The averages can be kind of meaningless when you start to look in a particular watershed or on a particular type of operation.
Yeah, well said. And that goes straight into the next thought I had for Greg. Greg, what do you think of merging the low level of tolerance that's prevalent among our farmers when it comes to nitrogen deficiency, and for good reasons, and employing Professor Nocera's microbial nitrogen to reduce N loss and enhance production?
I think all of those type of opportunities certainly make sense. It's exciting to see those type of technologies coming about, because we've always talked about nitrogen fixation in corn being that panacea that we would like to reach. And, certainly it would be impactful from, farmer adoption. I mean, that would be something very similar to GMO adoption if we had that opportunity.
Okay. Well, then how far are we before farmers can realize, or they can hold this as a product, Professor Nocera? Are we there?
Yeah, wait a minute. Yeah, I'm there. It's moving pretty quickly. There's a company that's already, it's done large field trials. Actually, with regard to the last question, it would be for Mark, who's at UC Davis. Some of our greatest pushes coming from California producers, and I thought there was a law on the books that they had to reduce their nitrogen by 50% in the not too distant future. And so we're getting pushed pretty hard by large producers in the Central Valley to deliver them a product within 2 years from now. And I don't know when that comes up, but I think Mark would know But that's generating a whole bunch of interest right now in reduced nitrogen in the Central Valley of California. And so I'm hoping within 2 years we'll have something.
So, my understanding is that there's not yet a requirement to say you have to reduce nitrogen by a certain amount, but it's a goal and there's an awareness and it's coming down the road. So I think some of the big producers are probably, smart to try to get ahead of the curve to think about what that is. And, there's also other laws that are coming into play there, like the Sustainable Groundwater Management Act, which has some water quality component too, in terms of looking at nitrate and groundwater. And in the San Joaquin Valley, the Southern Central Valley, really in many places throughout the Central Valley, but also especially the San Joaquin, nitrate and groundwater is a huge issue from a health perspective too. So yeah, I mean, it's no surprise. I think as a matter of fact, we know that larger operations tend to be able to push on the innovation side harder for reasons like they can do things at scale, economies of scale, and also because some of the larger operations that you may be working with, they have like agronomists on staff whose job it is to link with the science and bring it to the field. And then at the smaller scale farms, it might the traditional one farmer, one field, and a tractor, and they don't kind of have the capacity to uptake like the most cutting edge technology.
If I understand this right, Professor Nocera's invention would be scale independent. Doesn't matter whether you're a small farmer or a very large farmer, because I don't know how we can package this technology, but it could be in a bag. I don't know.
Yeah, it can be distributed. So the way it was designed to be very distributed, and but the sort of models we're thinking of is maybe a location, one location, and then it's produced there and just shipped locally. But it's a very distributed, that gets away from the large Haber-Bosch plant, which is like a lead weight. And so you're literally doing, like you said, and thank you for the title, it was better than I would have proposed. So it's literally Haber-Bosch on the fly. I mean, it's literally nitrogen coming out of the air, going right to the plant. So,
thank you. I have 2 hands up, Kit Franklin and then Greg. Kit?
Yeah, I was just going to follow up with something that came to mind about the previous question you put to me. I don't know about you in the US. Again, the numbers I was drawing from the Purdue retailer sort of survey show sort of a limited uptake by farmers, but here in the UK, where precision farming took off was by specialist retailers, specialist dealers who went into precision farming as their thing. The mainstream dealers of the big manufacturers weren't really interested at first. They were kind of scared by it. Didn't fit their skill sets as either sales or technicians. So it was really trailblazed by independent, smaller retailers to farmers. And it's only in the last 2 or 3 years now that the mainstream retailers have started, you can walk into most dealerships here in the UK now and there will be a precision farming specialist as part of the sales team. And that's a really recent addition to the John Deere or Agco dealership here in the UK. Before that, it was always done by independents. So that will have been somewhat to do with the uptake as well.
Okay, thank you. Okay, Greg?
Yeah, just a comment on current nitrogen prices as we start thinking about alternatives, that we're somewhere in the 35 to 45 cents a unit for nitrogen is kind of the competitive point. And then obviously we need to think about what that ultimate rate is, maybe less for other types of alternatives that could balance out that total cost that farmers would have to absorb in adoption of a new technology or competing technology to current fertilizers.
Thank you, Greg. I have a question popped up on Slack for Anna. What are the decomposition byproducts from the biodegradable sensors, and what would be the half-life of the materials that we're planning to use for those sensors?
Well, that's a very good question that unfortunately, as you know, Raj, we can't answer that yet. We are still investigating the materials that are biodegradable. So everything that I showed today was optimized for the performance so that we can really see how much we can monitor nitrate, and we also have moisture sensors. And now, today I didn't share any of the results with the biodegradable materials. And probably a year from now, I'll be able to answer that question way better, or answer at all. Sorry, I can't answer now. But we are looking at our goal. Our goal is to have the sensors be decomposed over time, not necessarily in one cycle of the crop, but for sure have the sensors not have communications after one cycle of the crop, so that if any sensor is left in the soil and it's not completely decomposed yet, it will not be giving data that is going to be going against the next crop of sensors. And so a lot of our work has been studying encapsulation techniques that will actually protect the sensors for long enough so that we can keep getting the data during the crop season.
Thank you, Anna. And while there's limited information that Anna can share right now, one of the things that came from the advisory board that this project has in place has to do with, well, if you distribute X amount of sensors out in the field, how do we go about collecting them and digging them back out from the soil at the end of the growing season? And that's really what led to making them inexpensive and biodegradable so that they fail after one crop cycle, and the material eventually decomposes over time, leaving very little to nothing in the soil. And what is left is actually part of what is naturally occurring in soil. So here's a question from Slack for Stephen. Is there anything more that can be done with conservation compliance lever to reduce nutrient loss and achieve other conservation goals?
Yeah, I haven't heard a lot of debate on this, but certainly conceptually you could reorient conservation compliance towards other issues beyond just erosion and beyond sort of the farmable wetlands and grasslands protection issues. So similar to the targeting question we had earlier, you could refocus the program towards some of these other issues if you could sort of identify which land is in and which land is out. And the other piece of it you'd have to add, right, is most of the planning now is focused on soil erosion control plans. And so you'd move over towards the nutrient management plans that we were discussing earlier, you know, and it would probably be the kind of minimal amount of nutrient management you'd want to get on the ground with that, right? Compliance tends to be the lower hanging fruit in terms of erosion control and soil health.
Okay. Thank you. Thank you. And I want to remind the panel that if you want to add more to the question that is directed to one of the panelists, you're welcome to chime in. I see a question that popped up for Professor Nocera here, and I think it builds on what was previously discussed briefly, that some nitrogen fixing plants can support high rates of leaching of nitrogen. Nitrogen is nitrogen, no matter how it comes from, whether it comes from soil or atmosphere. So as a part of your field trial, have you studied the field leaching rates with reference to your source of nitrogen?
No, and that's something we want to do, and we want to do it in partnership. So that's a good point. And also phosphorus, like I mentioned, if these organisms will take waste phosphorus and fix it as polyphosphate, so you can also put phosphorus into the plant. And really doing a good large-scale analytical chemistry of the soil has been missing. And I'll tell you the other thing missing is the microbial community. We're starting to work on that. But you're putting a lot of energy into the ground via this organism. I mean, you literally are putting energy into the soil. And so knowing how that works with its microbial counterparts, that also we haven't investigated much. It was just getting all the biology right has been consuming. I'm only an academic lab. But good analytical chemistry and microbial science of the soil needs to be done with this approach. And we're looking forward to partnering with people who would be interested in doing that with us.
Excellent. Roger, I have a question for you. You talked about N losses varies by practices, and that's widely documented. You're right. Given that poultry in the data that you presented, liquid swine and manure are the major contributors of N losses, right? They were at the bottom of your list in terms of where they fit in that spectrum of N sources that farmers rarely use in Midwest. What are your thoughts on utilizing, these N sources for crop production?
Well, I think, finding synergies in production systems, it's a great advantage to have the cropping and livestock systems together. There's uncertainty in all those pieces, land availability, where that production is, the concentration of it, the management of it, and then all the uncertainties that go with that. And in terms of the slide that had the nutrient loss reduction, that's that, and I would describe that as kind of version 1 compilation, and there's more research that has to be done. And I think that's going on right now. I mean, this is within the last 5-7 years of trying to establish how can we deploy performance measures to a landscape-based approach. But anyway, there's a lot of noise, right? And we're working in a variable system. But I have confidence that with the manure and the soils and everybody pulling in this way with research and technology, we can optimize and find the synergy. So I know that's not specifically answering your question, but that's where I think the answer lies.
Okay, Greg wants to add on to it, and in fact, I was about to ask Greg to chime in.
Yeah, what we've been doing, and actually it's led by Glenn Arnold here in the state, we've been doing in-crop application manure, somewhere around 5,000 to 6,000 gallons of swine manure going in crop, that replacing the total commercial need that we would have. Some of the challenges there are obviously weather to allow that to happen, the growth of the corn to get in there soon enough to not be, a lot of the efficiency is in drag lines, and we can only run those drag lines over the corn until they're about V3, V4 in size. There's some other technology that exists as far as allowing that drag line application to occur, that the hose runs down the rows. That opens up the window from 35 or so days to 75 days. So there are some opportunities out there to think about manures in a more nutrient strategic way, using them in crop for our type of application where that nutrient is used by that crop in season.
Thank you, Greg. Here's a comment or question for discussion for the entire group regarding in-field measurement tools of nitrogen. Due to complexity of nitrogen cycle and its interaction between plants and soil, it is apparent that more than one measuring technology needs to be employed to obtain an estimate of whether a plant has enough nitrogen in the system. We don't currently know the critical values of nitrogen for soil or plant sap throughout the growing season. let's say, for example, corn. How can we close that gap in getting this critical information?
Well, one comment I'd make is we just have to continue to invest in a multiplicity approach of research and you know, it's like you know, computers and data technology. I think we'll continue to you know, our ability to process that data is so much more today. But like Ken Castman talked about, the call for these bigger networks, that's what we're going to have, and I agree completely that we need kind of multiple sensors on the go, real time, artificial intelligence, remote sensing. You know, drainage comes into play, weather comes into play. You're going to have to deploy these smart networks of data technology. Precision agriculture is adding a lot to this. You're going to have to become very much more accurate, and we're going to have systems that are capable of doing the processing.
I would agree with you, Roger, that going forward, as we have access to the levels of quantification of nitrogen, as Anna is talking about, we will have no choice when you are receiving data in X and Y, Z depth, and time T, that we will have no choice but to incorporate algorithms that allow farmers to deploy near real-time decision-making process. I see Stephen wants to make a comment on that general question that we just mentioned. Stephen?
Yeah, I think I wanted to bring up this chart we've seen a couple of times now about the fact that uncertainty was kind of the third biggest barrier for adoption for a lot of farms. And so on that idea of sort of monitoring in multiple places, right? When that cost curve when those costs on monitoring get down far enough, there's a lot of potential private benefit for farmers to putting this monitoring in place, to getting rid of that uncertainty. And so this could be one of those technologies where actually the financial assistance isn't as critical, or it can be critical in an early stage while that cost curve is bending down. But as innovation occurs and as the production of these monitors scales up and costs come down, it could be one of those things you hit really widespread adoption, right? The private benefits here are really suggestive.
Thank you. Anyone else want to comment on the ongoing discussion? Greg?
Just add a comment that I think the ideal of things that KIT is working on as far as autonomous vehicles to be doing that practice out in the field really is, you know, the direction that needs to be headed. You know, doing some of these things across a 60-foot boom really don't work in relationship to try and bring them down to scale. So, you know, that ideal of autonomous vehicles or smaller application equipment running the field really makes sense in that application.
I would be looking forward to the day where we can use microbial Haber-Bosch produced nitrogen that we apply in the field, use Anna's sensor to measure how much is available to plants, and bring in KIT's technology to grow plants. And Greg, you're running the demonstration plots, right? How far are we from there?
Well, I guess from my element, we're not very far from the automation bit. You can have a small tractor with a small boom applying things and measuring things off of that boom today if you want. There's some legislation and legalities to work through, but technically we're there. Other companies, you know, working on this area. There's a company in the UK called Small Robot Company, and they now have robots in fields that are mapping individual plants and monitoring the growth of individual plants. I'm yet to be convinced there's a business case for that, but that's what they're developing, and it works. And even Google, you know, Alphabet are working in agricultural robotics. They announced a couple of months ago. So there's going to be a lot of big players entering this data capture, autonomous data capture space is going to be a big market going forwards.
Okay, I'm so pleased to see. I know there are at least a couple of farmers in our panel today, and I see that Rod Weimer has popped up. Rod, do you have thoughts that you want to share with us? You're muted, Rod.
Okay, can you hear me?
Yes, I can.
Okay, I like I say, we've cut our nitrogen usage back by, at least 50% doing what we're doing with drip irrigation and applying it at the root zones and whatnot. And I think as technology gets better, we're going to keep improving, and we're not seeing any runoff contaminating downhill streams. And yeah, that's my biggest thing right now. And we're trying our best to cut the use of nitrogen, cut back on that use, and we're achieving it. Even through center pivots, we're achieving that. So.
And Rod, maybe you want to give a flavor of, you're not doing this just on 1 or 2 acres. Just give us a flavor of the scale on which you have been able to accomplish this, and for how long.
Yeah, we've our first drip irrigation system was put in 1998, and we put it in a 200-acre field. And with that being said, we noticed better quality of our crops. Our main primary crop is onions, so we noticed better quality, higher yields, 30% less water, and 40 to 50% less nitrogen. And since then, we've added another 600 acres. So we've got about 800 acres in drip irrigation. And like I say, that the technology of drip irrigation is changing as we go. And they've got better emitters, and they're just doing a lot better job. And we got to kind of keep up with it as we go too. And this past year, we've replaced. So our drip irrigation is permanent. It's buried 8 inches deep, so we're doing the minimum till. We're not plowing our ground. We're keeping stubble. We're planting cover crops in the fall, so in the spring when we get our heavy winds, it doesn't blow away. And like I say, we just got to keep up with the times and use it as a tool, and also a way for us to survive. Right now in the Rocky Mountains, we're about 70% of snowpack. So we've got to use our water smartly. And this might be a survival for us.
So based on what you heard, Rod, today, where would you like to invest your time next? What are some of the promising things that you think about, or keeps you up at night, and you say, oh, I wish I could do this today. I could be so much better.
It goes back to your soil monitors, to monitor your soil, your moisture in a more effective way than what we have been doing. If you visualize your sprinkler system in your yard, that's kind of the way our drip irrigation works. So we have zones that we run for so many hours, and if we could run that with a soil moisture, it would really benefit us. And like I say, it would allow you to put your nitrogen on at a different time. It's a whole new ball field for us. I think I'm interested in that, and I think it's a way to also save nitrogen use. We're placing everything at the root zone, so therefore we don't have to put as much nitrogen on. Right.
Yep, good point. You're feeding right exactly where the plants will have access to that. I see that Steve Hoffman is in the crowd as well. If Steve, who farms in the Midwest area and practices there, wants to give some comments. And I noticed that Richard Wilkins would like to share some comments. You're muted, Richard.
Would you like me to share now?
Please. Please, and I noticed that Steve has come online too, and after that, maybe Steve can comment. Thank you.
So first here on our farm, I have to confess that I wouldn't say that we have reduced nitrogen usage. However, we have employed many tactics to be able to increase our volume of production with the same amount of nitrogen. So from that aspect, we're using nitrogen much more efficiently. Some of the ways that we're doing that is that our fertility system begins with being based upon renewable resource poultry litter. So poultry litter from commercial broiler production is the base of our fertility program. We like that because it's an organic form. It's more slowly released throughout the growing season, and because it only mineralizes and releases when the soil temperature is warm enough for it to mineralize. So we are not leaching out as much nitrogen when the soils are too cold for mineralization, and then we supplement that with other forms of nitrogen, and we're employing agrotine, which is a urease inhibitor treatment that we're putting on urea, and then for on corn, we're also including a polymer-coated urea as part of our blend that we're putting on our corn crops, so that we know that polymer-coated urea is not going to be immediately available, but it will be there for later usage. So in summary, from that aspect, we're optimizing our amount of nitrogen that we're using in order to get the most yield with the same amount. Now, one fear that I have with some of the the trend and the wave towards potential increase in regulatory requirements. I farm here in the Chesapeake Bay watershed, so we've seen some of that trend towards increasing the regulatory requirements, and then some of the especially precision agriculture types of tools. We've already seen a trend of a great deal of consolidation within our industry. And I guess my fear is that if we're not careful about how we move forward with better employing science to achieve success for the public good, the unintended consequence, I like to say that sometimes what consumers may be demanding, the unintended consequence is that there will only be a half a dozen people producing the food for them, and they may lose control over something that's extremely important, which is sustenance.
Thank you, Richard. Steve? So we got a glimpse from Rocky Mountains area and one from Chesapeake Bay. Steve, go ahead. We can't hear you, Steve. So it seems like we're having some technical challenges with Steve's voice. We could see him just fine, but his voice is not coming through. I know we're coming towards the very end of our panel discussion that we have. I want to take this opportunity to thank all the panelists and all the speakers that we have today. We have 2 additional workshops that are coming in the next 2 weeks. Before I pass the baton on, I see there's a hand that has gone up. Mark, you want to say something?
I was going to ask our farmer colleagues, who I'm very happy to hear from, what their main motivation would be for reducing nitrogen, whether it be cost or regulation or the public good. So I don't know if they have time for to talk about that or not, but that's the question I was going to ask.
Okay. Thank you.
What was that question
Mark?
again, Mark?
For your reductions in nitrogen that you have done, just was wondering what the main motivation was. Was it about cost or productivity or government policy, or it's just the right thing to do? That's kind of the sort of questions I'm interested in, at least.
Okay. For us here at Fagerberg Farms in Eaton, Colorado, it was about water, conserving water. It was about applying it at the right time, at the right place, and looking down the road at our children and grandchildren. I think it's going to be a must to improve our groundwater. That's our motivation. And we're, and like I say, we're still trying to implement things to make it better.
Thank you. And as a fellow Colorado, and I appreciate your attention to stewardship in my home state, at least.
Richard, you want to say something in response to Mark's question?
Well, sure. It's a very very good question, Mark. I'd have to say that in my case, it primarily it's resource management. It's first I'll say that on our farm we don't win yield contests. So our business plan has never been about pushing for maximum production. We tend to be more concentrating upon optimizing production so that we're achieving the greatest amount of output for each input of resource that we're applying. I had an ag economics professor that taught me about the law of diminishing returns, and in agriculture, because you don't have control over all of the factors of production, there's many factors of production that you have no control over. So we tend to stop at that point where one additional unit of input is likely to give us 3 additional units of output. So we don't win yield contests. So resource management, trying to optimize our profitability, and the sideline to the 3 pillars of sustainability. So that surely is we're concentrating primarily on the economic sustainability of our operation, but the other two legs of that stool, the environmental sustainability and the social sustainability, that allows us to be able to reply to those that are concerned about the way we are producing food for them, that we share the same values that they have.
Thank you, Richard, and thank you, Rod. I think, Mark, that was a very relevant question that you brought up, and I was very pleased that we were able to get answers straight from the people who are managing our agriculture and agriculture food systems. So I think this is a very good time for me to wrap up. Thank all the panelists and the speaker for today's workshop and pass the baton on back to Kathy. Thank you, everyone, for participating. Kathy, back to you.
Fantastic, Raj. Thank you. That was a terrific job moderating. Another incredibly filling day of information and idea sharing. So thank you all very much for being on the panel. I'm not going to spend any more time than to say thank you again, and to note that today was week number 3 from our webinar. And I hope that many of you can attend next week's webinar, which will be at the same time. You see flashed in front of you the lineup. We have, we're going to turn our focus to other ways designing programs to provide incentives for adoption. So Leah Palm-Foster is going to talk about paying for agro-environmental performance, basically paying for ecosystem services. Kurt Stevenson is going to talk about our experiences with water quality trading and the degree to which that might play a role. Kurt Waldman will focus on certification and supply chain standards, which has often a lot of discussion. We'll hear from the Nature Conservancy about their work on developing the market value of manure. And we've already heard from some of our farmers today, so you know that they will be well worth listening to next week when they have a panel and we can hear their reactions directly, and in particular, their ideas for how to move forward, what things need to be done. Likewise, we will have reactions from an action group panel that is from the Environmental Defense Fund and Sean McMahon from the Iowa Agriculture Water Alliance. So with that, I'm going to thank you and hope you can join us next week. Until then, stay warm across the country.